Okay, this is part 2 of the mini lectures on stellar structure and evolution. We said that the two main fusion reactions in main sequence stars are the proton-proton chain, which consists of 4 protons coming together to make a helium-4 nucleus plus energy, and the CNO cycle, the carbon-nitrogen-oxygen cycle, which is used for stars with mass more than about 1.1 times the mass of the Sun, and that is the dominant reaction in those stars. Proton-proton chain also occurs in the higher mass stars, and the CNO cycle often occurs in lower mass stars, but the dominant reaction, the one that makes the majority of the energy, is very, very closely related to the core temperature of the stars, and that's very closely related to the mass of the stars. So for main sequence stars, the upper half of the main sequence, beyond 1.1 solar masses, is almost entirely dominated by the CNO cycle, and the lower half below 1.1 solar masses is almost totally dominated by the proton-proton chain. Okay? And both of these are considered hydrogen fusion because they fuse hydrogen, protons basically, together to make helium. And that's another way of defining what a main sequence star is. A main sequence star can be defined as a star that burns hydrogen in its core, period. And that's it. That's the only process that goes on to create energy inside the only normal process that makes a main sequence star shine. Okay? So that is another way to define main sequence stars. That's also why main sequence stars are so well behaved. That's why the more massive ones are brighter and the less massive ones are less luminous. Okay. Now, you might think, well, can anything beyond hydrogen be fused to get energy? And the answer is yes. However, if you try to slam 2 helium nuclei together, you need a higher temperature because you need more speed, and you have to overcome a larger electrical repulsion. So it's more difficult to slam together heavier elements, heavier nuclei, to make even heavier elements than that. However, it does happen. Okay, but it doesn't happen in main sequence stars. So helium fusion occurs when a core temperature exceeds about 100 million degrees Kelvin. 100 million degrees Kelvin is hotter than even the highest mass main sequence stars, the ones at the tippy top of the main sequence, get to be. So you don't have any main sequence stars that have core temperatures of 100 million degrees. Carbon can fuse if you have 600 million degrees. There's no way you get anywhere near 600 million degrees in a main sequence star. However, those temperatures can occur in dying stars, giant and supergiant stars, as we will see in a little while. In very massive giant and supergiant stars that are in their sort of death throes, you could get temperatures high enough for even heavier elements than that to fuse. Silicon, oxygen, things of that nature. Okay. So, now let's talk a little bit about stellar structure. Why do stars exist? Well, a star is sort of in kind of a pause in between 2 collapses. We talked about earlier in the chapter, in the previous unit, how large clouds, molecular clouds of gas and dust, collapse under the force of gravity to make a star in the first place. Okay? Later on, we will see when a star runs out of energy, the energy that it uses to hold itself up, it will collapse again. Okay? But a main sequence star and even a giant and supergiant star are in a pause, a very long-term pause, sometimes taking billions of years, in between 2 collapses. The initial collapse to make the star and the final collapse at the end of the star's existence. Okay. Another way to think of it is, think of a star sort of like a balloon. Okay? In a balloon, you have gas pressure on the inside pushing out against the walls of the balloon, and you have the elasticity of the balloon's stretchy surface trying to make the balloon shrivel up. Okay? With a star, you have gravity trying to make the star shrivel up. Gravity is pulling inward very much the way elasticity is pulling inward in the balloon. Again, what you have is pressure pushing out. The gas pressure pushes outward, and that keeps the star from collapsing in on itself. Well, one of the basic relationships for gas pressure is that it's related to temperature. Okay? If you have ever had a bottle of soda that you drank halfway and then it gets warm, you put the cap on, you put it back into the fridge, sometimes you'll find that that soda bottle will collapse in on itself, will sort of shrivel up as the air inside contracts. That's because when the temperature decreases, the gas pressure also decreases. On the other hand, if you've ever picked up a basketball that's been standing out on a hot sidewalk and you bounce it, you'll find that it bounces higher than it would on a cold day. And that's because the gas pressure on the inside is greater once the basketball warms up. Okay, so pressure is approximately proportional to temperature as long as density doesn't vary much. The density of the gas also enters into this, but we're just going to use this as a very simple relationship. Basically, pressure and temperature go hand in hand. When one goes up, the other goes up. When one goes down, the other one follows. And that makes stars very stable. Stars have their own way of regulating their own nuclear reactions. This is something that textbooks often call the pressure-temperature thermostat. A thermostat in your house is something where you set it to a certain temperature, and if it gets higher than that temperature, the heat turns off. If it gets lower than that temperature, the heat turns on. Okay, so a thermostat tries to keep it at that static, the stat comes from static, tries to keep it at that static temperature that you set it at. Well, a star has its own internal thermostat. It's not an electrical device, obviously, but it's its own sort of regulator. It's a natural way that it regulates its nuclear reactions. Okay, so basically, all of the energy is created inside the core of the star. This outer portion is called the envelope, and it doesn't do much except insulate the star, insulate the core of the star to keep it nice and hot. You can think of this as a big downy blanket, keeping the core of the star nice and warm. If the reactions in the core of the star go too fast, it produces more energy comes out, and if more energy comes out, it heats up the envelope of the star. The envelope then, because temperature would go up, then pressure would go up and the envelope would expand. So a heated up envelope would expand. Expanding gases, however, cool off. Whenever a gas expands, and if you've ever let air out of a bicycle tire, you know that cold air seems to come out. Well, that's because the gas is expanding. Okay, when you have an expanding gas, the temperature goes down. If the temperature then of the core of the star goes down, the nuclear reactions will settle down and find their comfort level. Okay, so if the reactions go too fast, the temperature increases, which increases the pressure. This results in the star expanding and cooling off, which naturally slows down the reactions back to normal. Okay. On the other hand, if the core of the star isn't making enough energy, if the reactions proceed too slowly, the exact opposite will happen. The core will start to contract in on itself. Whenever you have a contracting gas or a compressing gas, it heats up. If you ever pump air into a bicycle tire and you hold the nozzle, you'll find that the more you pump the gas in, the hotter the nozzle will get. Okay, so when a gas is compressed, it heats up, so that will heat up the core of the star, and the core of the star will then produce more nuclear energy because of the higher temperature, and everything is then back to normal. So if the reactions go too slow, the temperature decreases, which decreases pressure. This results in the star contracting and heating up, which causes the reactions to speed up. Okay? So the star, in other words, finds its comfort level. It's this interplay between energy production, temperature, and pressure that causes the star to find a nice, comfortable state, a state where it is static, where it doesn't shrink, it doesn't expand, it's happy. It's a happy camper. Okay, there are 4 laws of stellar structure. These are actually mathematical laws that describe very carefully the internal structure of a star. We're only going to be describing it in a very qualitative way. Okay, we're not going to be going into a lot of mathematics or anything like that. So the 4 laws of stellar structure are used to describe the interior of a star. Now, one way that's very easy to visualize the inside of a star is to think of slicing open an onion. When you slice open an onion, you have these shells or layers of onion skin, okay, or onion layers, I guess. If you think of the inside of a star like that, you can think of each layer as having an average pressure and average temperature all the way around, okay? And that's the way astronomers sort of mentally imagine the inside of a star, that each layer has a particular temperature, pressure, and density that is pretty much uniform all the way around, spherically symmetric around the central core of the star. Okay. Now, the first law of stellar structure is really, really simple, and it sounds kind of almost stupid because it's so simple. But it's really important when you really do the math. It's kind of the accounting law of stellar structure. It's called continuity of mass. It says the mass of a star is equal to the sum of the mass of its layers or shells. In other words, it's almost like saying the mass of the onion is equal to the mass of this shell, and this shell, and this shell, and this shell, and this shell. So if you pulled it all apart and you weighed them all, you would come out with the same weight as the mass of the onion, as the weight or mass of the onion. Again, weight and mass are not the same thing, but I'm using them interchangeably here. You might say, well, duh, everybody knows that. But it's really important when you're making a computer model of a star that you have sort of a little computer accountant taking stock of what amount of mass you have in the star. Because if you end up with more mass than the star you wanted to model, or less mass than the star you wanted to model, then you don't have the same star. You have a different star. Okay, so if you're making a computerized mathematical model of a star, try to understand its interior structure, it's really important to keep track of the mass. Okay. Another law is continuity of energy. Okay. Continuity of energy says, basically, if you look at the layer of a star, the material, or rather the energy flowing into a layer of the star from below, plus the energy created inside the layer of the star, is equal to the energy that comes out. Okay, so this is pretty simple, really. And in fact, you hardly have to pay any attention to this except inside the core, because the envelope of the star really doesn't produce any extra energy. All the energy is produced in the core where the nuclear fusion is going on, but when you're modeling the star, you count up the layers, you count up the amount of energy that each layer produces, and you add that to the energy flowing into that layer from the bottom, and once you get to this area right here at the edge of the core, you basically have the entire luminosity, the entire energy output of the star. And the envelope is just there to transport that energy outward slowly and to keep the core nice and happily warm. Okay? So that is continuity of energy. Beyond the core in the envelope, where the temperature is less than 10 million degrees, very little energy is produced. Okay. All right, that is the end of part 2, and we will go on to part 3 next.